Alright, so class, we're going to start talking about Chapter 2, the chemical basis of life. Now, I'm hoping that a lot of this stuff should be fresh in your mind. Hopefully it's review from high school biology or chemistry or even physics. Alright, so we're going to be talking about basic chemistry. Alright, so start off with, we're going to talk about why we're discussing chemistry in the first place. Alright, so to understand how a cell functions, how it behaves. Alright, to understand the parts of a cell and what those parts do. Alright, this is tied in with the molecules that make them up. Alright, so for instance, we talked about the fact that every single living cell has a cell membrane. Every single cell has a cell membrane. Alright, so a cell membrane is made up of phospholipids. Alright, so here you have an image of phospholipids. Alright, so the phospholipid, right, has this little sphere here and these little tails coming off here. Well, notice that the sphere is located on the outside and these little tails are located on the inside. Well, why is that? Well, it has to do with the chemical properties of the atoms that make up that part of the molecule and how they're connected to one another through chemical bonds. So here, this little sphere is actually what we call particularly a phosphate group. Alright, so phosphate has phosphorus in it. Alright, so phosphate is something called a polar molecule. Down here you have your fatty acid tail. Your fatty acid tail is made up of a series of what we call hydrocarbons. Hydrocarbons are basically carbon atoms linked end to end and hydrogen atoms attached to them. Hydrocarbon. Well, hydrocarbons are non-polar. Alright, well, when something's polar, it's hydrophilic. When something's nonpolar, it's hydrophobic. Okay. Alright, so think about it. If something's hydrophilic, it means it's going to interact with, here, water. Alright, so that means that this portion of the molecule, that's phosphate's polar, it interacts with water. So that's why these little spheres stick out on the outside. Your tails are hydrocarbons. They're hydrophobic, fear, so they don't associate with water. They don't readily associate with water. Okay? They try to move themselves in such a way to get as far away from water as possible. Alright, so here you have your nice bilayer that makes up your cell membrane, because you have your phosphate head group and your fatty acid tails. Alright, so you get your double membrane structure. Alright, so talking about matter. What exactly is matter? Well, matter is anything that has mass and takes up space, right? So matter is made up of atoms and molecules. Alright, well, talking about atoms. What exactly is an atom? Well, an atom is basically the smallest particle, substance, that's representative of a particular element. Right? It retains all the properties of that element. All right, so here you have gold. You have a gold bar as a solid, and it's made up of gold atoms. All right, that gold atom retains the properties, the chemical properties, the identity of gold as an element. All right, so what about compounds? Well, compounds, like water, for instance, are made up of two different kinds of elements held together by chemical bonds. Usually this involves covalent bonds. All right, so here we have two atoms of hydrogen and one atom of oxygen. All right, so water, it's a compound. It's a molecule, but it's also a compound. Okay. So, thinking about these elements, all right, there are four elements that are important for living organisms because they make up a majority of us, for instance. All right, so you have carbon, you have oxygen, you have hydrogen, and you have nitrogen. All right, so these are the four major elements that are important. All right, so there are other elements that are also essential. All right, so things like phosphorus. Phosphorus, phosphates. All right, so phosphates are important in phospholipids. All right, they're important in DNA, RNA, and something called adenosine triphosphate. All these have in common phosphorus. All right, so it's a very important element. All right, and then we have our trace elements. Our trace elements are essential, but in terms of our diet, we only need a small amount of it. All right, so for instance, you have iodine. Iodine is important in terms of development of the thyroid. All right, so a deficiency in iodine leads to the enlargement of the goiter. Enlargement of the thyroid leads to a goiter. Sorry. All right, so think about it. We don't really see a lot of goiters in our country. And you don't see a lot of goiters in developed countries because of our diet. I mean, we have access to food. It's readily available. And there are many sources of food that naturally contain iodine. All right, eggs, berries, leafy greens, milk. But we also can purchase other products like salt. All right, so iodized salt. It's an easy supplement that we can use and get the necessary iodine we need every day. Now, think about when you go to the grocery store. You go to the grocery store and you pick up sea salt, right? It's healthier for you. But notice that sea salt on the label states that it's not a source of iodine. Alright, so you'd have to get it some other way in your diet. Okay. Fluorine. Alright, so fluorine, you have fluorinated water. Alright, you can purchase fluorinated water from the grocery store. A lot of times, city water is fluorinated. It's drinking water. And then you have fluorinated toothpaste. All these have fluorine in them because fluorine is needed for proper health of teeth and bone. And it's important for preventing, for instance, tooth decay and development of cavities. Alright, so here, looking at iron. Alright, so iron is another trace element. Alright, so iron is important in our diet because, for one thing, it's an important component of hemoglobin. Alright, so hemoglobin is the protein that's necessary to transport oxygen, and it's found in red blood cells. Alright, so looking at the molecule of hemoglobin, alright, later on we'll talk about protein structure, alright, but here you can see that hemoglobin, we have 4 subunits, alright, you have 2 alpha in purple and 2 beta in blue. And each of these has this little red sphere. Alright, so there are 4 red spheres. And these are able to bind to a pair of oxygen molecules each. Alright, so this is where oxygen binds. This is heme center. Okay? So individuals who are deficient in iron, they develop anemia. So you're weak, you're pale, you're lethargic, you're not energetic. Alright, you just all around don't feel good. Alright, because you're not transporting enough oxygen to your body. You have a deficiency in iron. Alright, so looking at compounds. Alright, so again, I talked about compounds and used water as an example. Alright, so compounds are typically more common in nature than elements. Now, the reason for this is because compounds, alright, atoms, you know, they're lonely. Alright, they don't really like to be all by themselves. Alright, so they like to interact with other atoms. So, other atoms of the same kind, or sometimes other atoms of a different kind. Alright, and the whole reason behind this is that they form chemical bonds and they're more stable. Okay? So, atoms like to make friends. Alright, so one example is sodium chloride. Alright, table salt. Alright, so think about what's used to make table salt. Well, sodium as an element and chlorine as an element. Well, sodium, naturally occurring solid, right? We have to extricate it from rocks, right? Mines. We have to mine for it. We have salt mines. Now, chlorine's a gas. Alright, it's noxious and toxic, deadly. Well, when you combine these two things together, you get sodium chloride. Alright, so you're taking something in nature, naturally occurring, you're taking something that's noxious and deadly, and you're using it to make something totally new, table salt, that has totally different properties. Alright, sodium chloride, alright, it makes different food products taste better. Alright, it enhances the flavor. But you know, too much of salt isn't a great thing, right? But it's not as deadly as chlorine gas, right? But this is a wonderful example of emergent properties. Sodium chloride has totally different new properties than sodium and chlorine. Alright, so what about the atoms? Alright, what about the parts of an atom? Alright, you'll want to familiarize yourself with this. Alright, where are the parts of an atom located? Alright, what do they do? Alright, so the nucleus of an atom. The nucleus of an atom, you have your protons and you have your neutrons. And outside the nucleus, you have your electrons. Well, your protons have a positive charge. Alright, so they also determine what element an atom belongs to. Alright, so the number of protons. So like hydrogen. Hydrogen has 1 proton. Alright, hydrogen is hydrogen because it has 1 proton. Helium has 2 protons. Alright, helium is helium because it has 2 protons. Alright, so the number of protons determines the element. So if you change the number of protons, you change the element. Okay? the neutrons, as the name implies, is neutral. Alright, no charge. But it determines the isotope level of a particular atom. Alright, so think about this. You have isotopes. You have isotopes of hydrogen. You have isotopes of carbon. You have carbon 12, 13, 14. Well, all of these are different versions of carbon as an element in nature. Alright, they're all isotopes. They're all carbon. They all have the same number of protons, just a different number of neutrons. They're isotopes. Alright, so electrons. Electrons, alright, they have a negative charge. Alright, so to remember this, that electrons have a negative charge, think about electrons and electricity. Think about electricity, you get shocked. You get shocked, that's a negative response. So electrons have a negative charge. Alright, so electrons, why are they important? Well, they are the parts of an atom that participate in chemical reactions. Alright? They determine the overall behavior of an atom. Alright, so we'll touch on electrons a little bit later. Alright, first we're going to focus on each particular type of atom and some terminology, alright, when you're looking at the periodic table. Alright, so, looking at elements in the periodic table. Alright, so a lot of times you'll notice when you look at the periodic table, you have information that's portrayed as seen. Alright, so you'll have your element, you have a symbol for your element. Alright, below that symbol you may have the name. Okay, and out to the side you have like a subscript and superscript. Alright, the subscript, Z here, represents the atomic number. The superscript, A, in this example, represents the mass number. Well, what does the atomic number of an element mean? What does it tell you? What type of information can it provide? Well, the atomic number tells you the number of protons and the number of electrons found in an element. The atomic mass. The atomic mass, or mass number, they're roughly equivalent, okay, for all intents and purposes. They are determined by the number of protons and neutrons in a nucleus of an atom. Well, think about that. The bulk of an atom is made up of its protons and neutrons. The mass of it, the nucleus. Alright, your electrons have what we call negligible mass. Okay? So, when you're talking about the mass number, or atomic mass, it's basically the addition of protons and neutrons. Alright, so here, I'm giving you an example. Alright, helium, symbolized by He. Alright, so how many protons are there found in an atom of helium? Well, to figure this out, look at the atomic number. The atomic number is 2. Alright, so the atomic number is 2. That tells you that you have 2 protons. Alright, now, how many electrons does it have? Well, the atomic number tells you you have 2. You have 2 electrons. Now, what about those pesky neutrons? Well, here's what you do. Since the mass number is the number of protons plus the number of neutrons, alright, what you do is you basically would take here 4, which is your mass number for helium, minus 2, which is your atomic number, and you're left with the number of neutrons, which is 2. Alright, so moving on to another example. Carbon. Alright, so carbon, alright, has an atomic number of 6 and an atomic mass of 12. Alright, so how many protons are found in an atom of carbon? Well, based on the atomic number, it's 6. Well, what about the number of electrons? Alright, well, also 6. Right, the atomic number is 6. Now, what about the number of neutrons? Alright, sorry. Should be carbon. Alright, so how many neutrons are found in an atom of carbon? Well, here you have the mass number, or atomic mass, which is 12, minus the atomic number, which is 6. So 12 minus 6 gives you 6 remaining neutrons. Okay, so there are 6 neutrons in carbon, in an atom of carbon. Alright, so what about silicon? Alright, so silicon has 14 protons, 14 electrons, and 14 neutrons. So, what if we look at it in the opposite direction? Instead of giving you the atomic number and atomic mass, I'm going to have you calculate it. Alright, so the atomic number. Well, atomic number tells you what the number of protons or number of electrons in an atom. So, since we have 14 protons, this tells you that we have an atomic number of 14. Alright, so the atomic number would be 14. Alright, so what about the atomic mass? Well, the atomic mass is protons plus neutrons, right? Alright, so 14 protons, 14 neutrons gives you an atomic mass of 28. Alright, so a lot of times talking about atomic mass, just kind of talk about units. A lot of times it's designated as AMUs, or atomic mass units, or another term would be things like Daltons. Okay. Alright, so looking at another example, we have aluminum. Alright, so what is the atomic number of aluminum? Alright, so here, looking at this image of the basically atomic structure, cartoon atomic structure of aluminum. Alright, so what is the atomic number? Well, notice here that if you look at the protons, little yellow spheres, you have 13. Alright, so 13 is the atomic number. Alright, so what about the atomic mass? Well, notice here you have 13 protons and 13 electrons. Alright, so that's 26. Alright, so now we're going to transition. Alright, we're going to talk about isotopes. Alright, so isotopes. Isotopes are going to have the same number of protons, but a different number of neutrons. Alright, so in nature, alright, when you're talking about, for instance, hydrogen, alright, which we'll talk about the isotopes of hydrogen in the next slide or so. Hydrogen in nature, alright, it doesn't exist always as hydrogen with one proton, one electron. Alright, a majority of the hydrogen in nature does exist like that, but there are other versions of hydrogen, other isotopes of hydrogen. Alright, so there are two. Alright, deuterium and tritium, which we'll talk about a little bit later. But there are three versions or isotopes of hydrogen. Alright, they're all hydrogen. They all behave like hydrogen. Alright, when you're drinking water, alright, you're drinking hydrogen. You're drinking a little bit of deuterium and a little bit of tritium. The majority of it is regular old hydrogen. Okay? Now, what differs between those three is the number of neutrons. Alright, so I like to think about isotopes as different flavors of ice cream. Alright, they're all ice cream, but they're all a little different. You have chocolate, you have vanilla, you have strawberry, you have peach, you have mint chocolate chip. They're all ice cream, but you have different versions of them. Alright, so when you're looking at, for instance, uranium. Alright, I mean, we all know that uranium is radioactive. Alright, so there are isotopes of uranium. Alright, so here we're given the atomic number 92. So notice between these two isotopes of uranium. Alright, so uranium-235, uranium-238. Alright, they're both uranium. Well, why are they both uranium? Well, they're both uranium because they have the same atomic number, 92. Now, what's the difference between these two? Well, the difference is the total number of neutrons found in the nucleus of that atom. They have different atomic masses. So look at the mass number, or the atomic mass, 235 and 238. Well, if the number of protons remains the same, that would imply that the number of neutrons is what varies. Alright, and in fact, that's what it is. Alright, so uranium-235 has 143 neutrons. Uranium-238 has 146 neutrons. Alright, so here, looking at xenon. Alright, so xenon. Alright, xenon has an atomic number of 54. Alright, so 54 protons. And what about number of electrons? Well, it has 54 as its atomic number, so 54 electrons. Mass number would be, in this case, 108 minus 54, which gives you 54. Alright, so going back to isotopes. Sorry for that little transition in the slides. Keeping you on your toes. Think of that as a review question. Alright? Alright, so back to isotopes. Alright, so here, alright, talked about that you have three isotopes of hydrogen. Alright, so hydrogen 1. Alright, this is the most abundant in nature. Alright? Now, you also have two other isotopes. You have deuterium and tritium. Alright, so hydrogen has one proton, one electron. Its atomic mass is 1. So hydrogen 1 doesn't have a neutron. Alright, so that's why its atomic mass is 1. Alright, because the only thing that's contributing considerable mass to that particular atom is its proton. Alright, so deuterium. Deuterium has one proton, one neutron, and one electron. Alright, so it's still hydrogen. It's still hydrogen because it has one proton. But it's an isotope of hydrogen, alright, because it has a neutron. Alright, so it has an atomic mass of 2. And tritium has one proton, so it's still hydrogen, but it's a different version of it. It has one proton, 2 neutrons, and 1 electron. So an atomic mass of 3. Alright, so getting back around to isotopes. Isotopes of a particular element behave the same in chemical reactions. Alright, well, think about this. What determines the chemical behavior or reactivity of an atom? Well, that's the electrons. Alright, well, in this case, hydrogen, deuterium, and tritium all have one electron because their atomic number is 1. Alright, so they're all going to behave the same. Alright, so what's contributing to the difference in terms of the mass is the neutrons. Alright, so looking at carbon. Alright, so I talked about carbon 12, 13, and 14 as examples of isotopes. In this case, alright, carbon. You have carbon 12, 13, 14. Well, what's the difference between these three? Well, look. You have 6 neutrons in carbon 12, 7 and 13, and 8 and 14. Alright, so it's the difference in neutrons. These are all examples of carbon that are found in nature. You're more familiar with carbon 12. Alright, but there are other versions of carbon in nature, some of which are radioactive. Alright, something like carbon 14. We use carbon 14 for dating, carbon dating, fossils. Alright, each of these versions, isotopes, they all behave like carbon because they all have the same number of electrons and they all have the same number of protons. Alright, the same number of protons means that it's the same element, so it's carbon. Same number of electrons means that it behaves the same way. Alright, so here's an example. Alright, you have oxygen 16 and oxygen 18. Alright, they're isotopes of oxygen. Alright, so I'll tell you. The atomic number of oxygen is 8. Alright, so what is the number of neutrons in oxygen 16? Well, here, the atomic mass of oxygen 16 is 16. Okay, so what determines the atomic mass? The protons and neutrons. Alright, so 16 minus the number of protons, the atomic number, 8, gives you the number of neutrons, 8. What about oxygen 18? Oxygen 18, atomic mass of 18. Alright, minus the number of protons, 8, gives you 10 neutrons. Alright, so oxygen 18 has 2 more neutrons than oxygen 16. Alright, so talking about electrons. Alright, so electrons are outside orbiting the nucleus of an atom. Alright, so they exist in different levels, what we call shells, electron shells. Alright, so these shells are what we often refer to as orbitals. Alright, orbital shells are interchangeable. Okay? Now, when you're talking about shells, alright, the electron shell that we are the most interested in, alright, is the outermost electron shell. Alright, the number of valence electrons are found in the outermost shell. Alright, so here, looking at hydrogen for instance. Hydrogen, alright, it's got one shell outside its nucleus. All right, it's got one electron. All right, so it has one valence electron. Carbon in its outermost shell has 4 valence electrons. All right, so looking at nitrogen. All right, nitrogen has 1, 2, 3, 4, 5 valence electrons. All right, oxygen has 1, 2, 3, 4, 5, and 6 valence electrons. All right, notice here that you have these vacancies, right? These vacancies represent spaces of unpaired electrons. All right, so like I said, atoms like to be friends with other atoms. All right, they don't like to be alone. All right, so in this case, all right, electrons always pair up. All right, they're pairs. They're partners. Okay, so basically each of these vacancies represent a pair that hasn't been formed yet. All right, and we'll talk about what that means a little bit later. All right, so thinking about the electron shells. So here you have your first shell, you have your second shell, and you have your third shell. You're of a hypothetical atom. Okay. Now, when atoms absorb energy, all right, electrons can actually be boosted from a low energy level to a higher energy level. All right, because they're absorbing energy. Okay? And then what they'll do is they'll fall back down to ground state. All right, so for instance, when you see a firefly at night, all right, you're seeing a chemical reaction take place. Electrons are excited, and then they fall back down to ground state. Okay? As you move further away from the nucleus of an atom, all right, so remember, the nucleus of an atom, you have protons, which have a positive charge, and your electrons have a negative charge, right? Well, think about it. Positive and negative charges are attracted to one another, right? So the further you get away from the nucleus of an atom, the less hold, the less pull the nucleus has on it. All right, so you have a strong attraction between electrons in the first shell and the nucleus. And the further away from it is from the nucleus, the higher amount of energy at that level. All right, there's less of a pull between the nucleus and the electrons. So there's a higher amount of potential energy. Okay? So here you're given a diagram of a ball falling down the stairs. Alright, so think about it. If you fall from just this first step down, there's a small amount of energy. But if you fall from the top stair, down, 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 alright, there's more energy. Alright, what hurts worse, falling down one step or 3? Alright, I mean, chemically, that's not going to make a lot of sense, but it's getting the point across. The higher or the further away you are from the nucleus of an atom, the more potential energy the electrons have. Okay? There's more stored energy in them. Alright, so looking at the periodic table. Alright, the periodic table. can give you a whole lot of information. Alright, so here you're looking at an abbreviated version of the periodic table. Alright, so here, looking at, for instance, hydrogen and helium. Hydrogen and helium, there is a relationship between these two elements. Well, all of the elements on the first row, look, they only have one shell. Alright, so the row that an element's found on tells you the number of shells. Alright, so number of shells, of electrons, electron shells. Okay. When you look at the column, alright, when you look at the column that elements fall on, it tells you the number of valence electrons. Well, hydrogen, lithium, and sodium. These are all three different elements. They all have three different numbers of shells. Alright, but they have one valence electron. Alright, the electron is found in the outermost shell. Here. 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 Alright, so the columns tell you the number of valence electrons. Alright, now for what you're seeing here, this is always going to hold true. There are a lot of exceptions to the rules. Alright, so notice that you don't see some of your transition metals here. You don't see your metals, your metalloids anywhere here because they're weird, they're funky. Alright, and they don't behave like this. Alright, these guys are a little bit more predictable. They follow this trend in the periodic table. Alright. Alright, so valence electrons. Alright, valence electrons are those in the outermost shell or valence shell. Alright, the chemical behavior of an atom, alright, is going to be determined by the valence electrons. Alright, so going back to the previous slide, alright, notice here, it says that if, for an element, if it has a full valence shell, it's chemically inert. Well, go back. Let's look at helium, neon, and argon. Well, helium, neon, and argon, they all have a full valence shell. Helium has 2 electrons in its first shell, neon has 8, and argon has 8 as well. Alright, so it has a complete outer shell. Alright, it has a complete, what we call, octet. Okay? So, the octet rule. Alright, the octet rule is about, basically, the number of electrons that can be found in each orbital, or shell. Okay? So, looking at the first shell. The first shell can hold a maximum of 2 electrons. The second shell, 8. Third shell, 8. Alright, so this is what we'll be dealing with a majority of the time is, 3 to 4, maybe 2 to 3 to 4 shells max. Okay? So, here, alright, these are inert. Alright? They're chemically unreactive. Alright, because they have a full valence shell. Alright, the reactivity, alright, going back to the point I made earlier, the reactivity is determined by the number of valence electrons. So if you have vacancies, if you have unpaired electrons in the outermost shell, those atoms are going to try and interact with other atoms to fill their valence shell. Right? So since these are inert, they already have a full valence shell, they don't react with other elements. Alright, so looking at this octet rule. All right, so lithium. Lithium has three electrons. Okay, the first two electrons fill the first orbital. The last electron fills the last orbital, the second shell. All right, so it has one valence electron. Looking at carbon. All right, carbon has 6 electrons. All right, so when you're looking at carbon, it has 6 electrons. All right, so when you look at the nucleus here, all right, you have shell, first shell. All right, it gets 2 electrons. All right, well, since there are 6, you're left with 4. Well, you have your second shell. You have 1, 2, 3, 4 valence electrons. All right, so these would be your valence electrons here. Alright, so looking at magnesium. Alright, so how many valence electrons does magnesium have? Well, look here. You got 1, and you got 2 in the outermost shell. So 2 valence electrons. Alright, so looking at something we'll talk about in a couple of slides, Lewis dot structures. Alright, so a Lewis dot structure is nothing more than its symbol, chemical symbol representation, and a representation of the number of valence electrons. Alright, so this is a Lewis dot structure. Alright. So here you have 2 valence electrons. Alright, so what you do is you have 1 electron there, 1 electron there. Alright, this represents the electrons, the valence electrons for that particular atom. Alright, so looking at hydrogen. Alright, so hydrogen has 1 valence electron. Alright, so you have the chemical symbol H and a little dot. Alright, this represents, alright, its valence electron. Alright, so thinking about valence electrons. Alright, you have 1 valence electron in 1 atom of hydrogen. Right? Alright, 1 valence electron. And then you have another little hydrogen that comes along. It has 1 valence electron. Well, when those 2 come together, alright, you get the formation of a molecule of hydrogen gas. Alright, so you have a single bond holding these 2 atoms together. You have a shared pairing of electrons. Alright, so Lewis dot structures are useful. Alright, so this is why we're going over them. Because to understand chemical bonding, you have to understand valence electrons and how they're either shared or donated between atoms. Alright, so that's what makes these things so useful. Alright, so what about nitrogen? Alright, so nitrogen, it has atomic number 7. Alright, so here in this representation down at the bottom, you have 2 electrons that fill the first shell. Alright, so you're left with 5. Alright, so you have 5 valence electrons. Alright, so how do you represent this using a Lewis dot structure? Well, it's kind of like a compass. Alright, so you have a north, east, south, and west surrounding your little symbol for your element. Alright, so all you do is place a dot here, for instance, here. So east, south, west, north. Alright, so you have 4. Alright, now you can have on each side of the element, on east, south, west, and north side of an element, where the symbol is, you can have 2 electrons that fill that spot. The electrons pair up. Alright, so where does the 5th one go? Alright, well, it can go here, for instance. Alright, so this shows you the Lewis dot structure for nitrogen. Alright, so below here, you have examples of a couple of other different elements. Kind of give you examples of other Lewis dot structures. Alright, so for instance, what about boron? Alright, boron. You have 1 valence electron, 2 valence electrons, 3 valence electrons. Alright, silicon, Si, you have 1, 2, 3, 4 valence electrons. Alright, so here, looking at silicon again. Alright, you have atomic number 16. Alright, so you have 2 electrons that fill the first shell. Alright, you have 8 that fill the second shell. Alright, so you're left with 6. Alright, so here you have 1, 2, 3, 4, 5, 6. Wait, that's wrong. Alright, so looking at carbon. Alright, so carbon, how many valence electrons are there in carbon? Alright, you have 4. What about oxygen? You have 6. Alright, so here you have the Lewis dot structure of carbon and oxygen. Alright, so this kind of tells you how to use your Lewis dot structures to figure out what carbon monoxide will look like. Alright, so carbon and oxygen. Alright, so you're going to be sharing electrons between these 2 particular atoms. Alright, so 2 electrons in a bond. Alright, so basically what you have is, since here carbon has 4 and oxygen has 6 valence electrons. Alright, that means that carbon has 4 vacancies, right? It needs 4 pairs of electrons to be complete. Oxygen needs 2 pairs of electrons to be complete. Alright, so here, alright, what you have is a physical representation of what these structures would look like. So carbon, you have 1, 2, 3, 4 valence electrons. And oxygen, Right, you got 1, 2, 3, 4, 5, and 6 valence electrons. Alright, so they can interact with one another to form chemical bonds. Alright, so sharing electrons, they can form a chemical bond. Alright, so basically you have to fulfill the octet rule. Alright, so the idea here is that by sharing one pair of electrons, alright, you get a single bond. Alright, that means that carbon, at only one period of time, is going to have 1, 2, 3, 4, 5 electrons. And oxygen would only have 1, 2, 3, 4, 5, 6, 7 electrons. Well, that's not a full octet. Alright, because they're still not sharing the ones that they need. Alright, so then what you would have is another pair of shared electrons. Okay, so you get what we call a double bond that forms. Alright, so that would be 1, 2, 3, 4, 5, 6 electrons that would be shared with carbon, but then oxygen would have 1, 2, 3, 4, 5, 6, 7, 8. But still carbon doesn't have enough. Alright, so here you end up with basically the formation of a triple bond between carbon and oxygen. So you have a full, complete octet. Alright, so carbon monoxide, alright, for instance, involves carbon and oxygen forming a triple covalent bond between two atoms. Alright, so they're basically sharing a total of 6 pairs, 3 pairs of electrons each. So a total of 6 electrons. Alright, so looking at carbon and hydrogen. Alright, so again, carbon, how many valence electrons? Well, you have 4. Hydrogen, 1. Well, let's look at the formation of what we call ethane. Alright, so ethane would be basically C2H4. Okay, so here you have 2 carbon atoms and 4 hydrogens. Alright, so you have the interaction between 2 carbon atoms. Alright, they share 2 pairs of electrons. Alright, so a double bond. And then each hydrogen atom gets 1 electron each. Alright, so everybody's happy. Oxygen gets 1, 2, 3, 4, 5, 6, 7, 8. Or carbon gets 1, 2, 3, 4, 5, 6, 7, 8 electrons. This carbon gets 1, 2, 3, 4, 5, 6, 7, 8 electrons. Each hydrogen atom gets 2 electrons. So everybody's happy. Everybody's octet is full. You have a stable molecule. Alright, so your electron orbitals. Alright, thinking about orbitals or shells. Alright, now they're represented as rings on a cartoon figure, but in reality, they're not rings. Alright, these orbitals take up 3-dimensional space, and they are a representation of where those particular electrons would be any given point in time. Alright, so look at your first electron shell. Alright, here. Alright, your 1s orbital. It can only hold 2 electrons. It's a sphere. Alright, so S, spherical. Your second shell, alright, it can hold 8 electrons. So the 2s orbital, it's spherical, it'll hold 2 electrons, and then you're left with p orbitals. Alright, so p orbitals are like lobes, alright, and you have an X, Y, and Z axis. Alright, and so these other electrons, alright, at any given point in time can either be the X axis, the Y axis, or the Z axis. Alright, they could be anywhere in this three-dimensional space. Alright, but these orbitals can only hold a certain number of electrons. Alright, so now we're going to talk about the formation of chemical bonds between atoms. Alright, so I talked about before where atoms, you look at their valence shell. Well, if they have a vacancy in their valence shell, so the first shell you have to have 2 electrons, right, to fill it. The second shell 8, third shell 8, and so on. Well, if you're missing a full shell in terms of the number of electrons, then it's incomplete. So this is where you have the formation of chemical bonds. This is when atoms interact with one another and join. Alright, so the first chemical bond we'll talk about is a covalent bond. Alright, so covalent bonds involve the sharing of electrons. The sharing of a pair of valence electrons by 2 atoms. Alright, so the sharing of valence electrons between 2 atoms, you form a molecule. Alright? Formation of a covalent bond between 2 atoms, 2 or more atoms, forms a molecule. Alright, so here I gave you the example of hydrogen. Alright, you had hydrogen, 1 valence electron, hydrogen, 1 valence electron come together. Alright, the chemical reaction to form hydrogen gas. Alright, so they're sharing electrons. They're sharing a pair of electrons. And they're happy. Alright, so getting back to that idea I mentioned before that most of your particular elements don't exist in nature by themselves. They form compounds and molecules. Well, you have hydrogen gas, for example. Alright. So when you talk about sharing of electrons, what that means is that the electrons are moving back and forth between one atom and the other. Alright, so notice here, alright, talking about these electrons moving back and forth between one atom of hydrogen and another atom of hydrogen. Alright, well, they're being shifted between one atom to the other equally. Okay? So an equal sharing of electrons. What that means is that the electrons spin the same amount of time around each atom. Alright, so atoms can share different pairs, number of pairs of electrons. So if you share one pair, we call that a single bond. If you share 2 pairs, double bond, 3 pairs, a triple bond. Alright, so here you have, for instance, methane. Alright, so methane, the carbon atom has 4 valence electrons, meaning it has 4 vacancies. So that means you can pair up with 1 hydrogen atom per vacancy. Alright, so you can get CH4, methane. Here, carbon dioxide, which we talked about previously, or we talked about carbon monoxide forming double bond. Here you have carbon dioxide. Carbon dioxide also forms double bonds. So it looks a lot like that. Okay. So you're sharing 2 pairs of electrons here and here. So everybody's got a full valence shell. And then nitrogen. Nitrogen is held together by a triple bond. So you're sharing 3 pairs of electrons. So you get a triple bond. Right, so the sharing of a single, double, or triple pair of electrons has to do with filling the valence shells of the respective atoms. Alright, so what's the difference between a molecule and a compound? Alright, well, molecules are any combination of 2 or more elements forming a covalent bond. Well, you get a molecule. Alright, but here, alright, not all of your molecules are compounds. Alright, compounds involve the combination of 2 or more different elements. Alright, so nitrogen oxide, water, carbon dioxide, carbon monoxide. All of these are compounds. Hydrogen gas, oxygen gas, chlorine gas, nitrogen gas. These are molecules. Nitrogen oxide is a molecule. Water is a molecule. But only this bottom row are examples of compounds. Alright, so looking at something called electronegativity. Alright, so electronegativity is all about how strong an atom pulls on its respective electrons. Alright, the attraction of an atom for electrons. Alright, some atoms are more greedy than others. Alright, so in this case, some atoms have a stronger pull on electrons and they are highly electronegative. Other atoms are going to not have as high of electronegativity and they have what's a partial charge. Alright, so think about this. You have 2 atoms. Alright, what's in the nucleus? Well, protons. What's outside the nucleus? Well, the electrons. Well, in this case, if an atom has a stronger pull on electrons, alright, it's pulling those, maybe it's sharing electrons with another atom, but it's pulling those electrons strongly and holds on to them more. Well, for a period, it's going to have basically more electrons than it does protons. So for a period of time, mind you, and it's going to be electronegative. You get it's a partial charge, partial negative charge. And then the other atom that's involved, well, since it's losing its electrons to the more electronegative atom, well, it has one more proton. So it's, for a period of time, partially positive. So it's a partial positive charge. Right, so you can use this chart of electronegativity to figure out what type of chemical bond is going to form between 2 respective atoms. Alright, so this is a very helpful chart. Alright, so for instance, walk you through a few problems. Alright, so here, alright, you have 3 different types of chemical bonds. You have nonpolar covalent, polar covalent, and ionic. And we'll get to what these mean in the next couple of slides. Alright, but just to label them as which is which. Alright, so here you have hydrogen gas. Well, hydrogen gas has an electronegativity of, let's see here, 2.1. So an electronegativity of 2.1 minus the other hydrogen atom, 2.1, gives you 0. Well, if you're less than 0.5, that's a nonpolar covalent bond. Alright, so hydrogen gas is held together by a nonpolar covalent bond. Alright, well, what about hydrochloric acid, or HCl? Alright, well, the chlorine has an electronegativity of 3. Alright, so chlorine minus 2.1 for hydrogen gives you 0.9. Well, between 0.5 and 2.1, you have a polar covalent bond. And then sodium chloride. Well, sodium and chloride, sodium chloride, you have sodium atom, you have chlorine atom. Well, sodium has an electronegativity of 0.9. Chlorine, 3. Alright, so this is 2.1 and greater, then it's an ionic bond. Alright, so this is where you get your ions. Alright, in other words, one atom has such a strong attraction for electrons that it effectively keeps it. It steals it. It never gives it back. Alright, so we'll talk about nonpolar, polar, covalent bonds, and ionic bonds in the next couple of slides. Alright, so here, talking about nonpolar covalent bonds. Alright, a nonpolar covalent bond. Alright, so you have two atoms, and the electrons are being shared equally. Alright, so notice here, their electronegativity is the same, alright, for hydrogen gas, because they're the same atoms involved forming the molecule. Alright, well, it's a covalent bond, but the electrons are going to spend half their time around this atom and half their time around the other hydrogen atom. Alright, so they're equal and they're sharing. Alright, but water, for instance, this chemical bond and this chemical bond is a polar covalent bond. It's a covalent bond because it involves the sharing of electrons, but it is polar because there's a polarity. There are poles, like a north and south pole on a magnet. Alright, you have a positive end on a magnet, you have a negative end on a magnet. Alright, so here, alright, oxygen. Oxygen has an electronegativity of what? 3.5. Alright, so let's see, 3.5, and you have 2.1 for hydrogen minus 2.1. Well, that gives you what? 1.4. So 1.4 falls between 0.5 and 2.1. So this is a polar covalent bond. Alright, but look at the periodic table. Alright, now oxygen is highly electronegative. Alright, so is nitrogen, so is oxygen, so is its fluorine. Alright, so these are high electronegative elements. Alright, have a strong pool of electrons. Alright, so what's happening here is that you have oxygen and you have hydrogen, and basically the oxygen atom is stealing the electrons from the hydrogen atom. Alright, it's not sharing the electrons equally with the hydrogen atom. Alright, they're still shared, but the oxygen atom doesn't want to play fair. Alright, so it holds on to them more strongly. Alright, so that's why this gets a partial negative charge and your hydrogens get a partial positive charge, because for a period of time the oxygen atom has more electrons than it does protons, so it gets a slight negative charge. And then your hydrogens are losing those electrons, so they get a slight positive charge because they have more protons. Alright, so These are partial charges because they're not full. Alright, because the electrons are still being shared, just unequally. Alright, so here you're given various examples of nonpolar and polar covalent bonds. Alright, so now look here. You're looking at just one part of the water molecule. Alright, but here you have hydrogen and oxygen. Notice that the oxygen atom much bigger, and it has a stronger pull on the electrons. Notice that the electrons are spending more time around the oxygen atom than around the hydrogen. Alright, so this is showing you basically how strongly these electrons are being pulled toward this particular atom. It's kind of like a map. Alright, so it's enlarged because there's a stronger pull. It's a larger atom. And the electrons spend more time around the oxygen and less time around the hydrogen. Alright, so looking at ions. Alright, so your ions would be atoms and molecules that have an electrical charge. Alright, and this electrical charge has to do with either donating or receiving electrons. So they either give up electrons, they donate them, or they accept them and they gain them. Alright, so when an electron is lost, an atom has a positive charge. Alright, so this would be your cation. And then when an electron is gained, you get a negative charge. Alright, that's referred to an anion. Alright, so now you have some atom that has a positive charge, some atom that has a negative charge. Alright, it is the electrostatic attraction between these different charges that holds the two atoms together. It isn't the donating and receiving of electrons, but the difference in charges. The difference, alright, that holds these two together. They're opposite in charge. So it's an electrostatic attraction. Alright, so here you have sodium. Alright, sodium has one valence electron. Alright, the chlorine atom, alright, it has 7 valence electrons. Alright, so the sodium atom gives up 1 electron, its valence electron, it donates it to the chlorine atom. And now sodium has 1 more proton than it does electrons. Alright, because look, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 protons. Well, here, if you look at chlorine, you have 1, 2, you have 8 in the second shell, so that gives you 10, and gives you a total of 17 protons. Alright, so now, when you look at the number of electrons, well, initially you have 11 electrons in sodium, and you have 17 electrons in chlorine. Alright, well, what happens when you have this donation of electrons from one atom to the next? Well, you end up with now having 10 electrons in sodium, and you end up with having 18 electrons in chloride. Alright, so this is why, since this has a positive charge and this has a negative charge, because you have 17 protons, alright, you get these charges. Alright, so you have one more proton in sodium than you do electrons. So you get a full positive charge. Alright, you get a +1 charge. In chloride, you have one more electron than you do protons, so you get a -1 charge. Alright, so this is how you get Na plus Cl minus, so sodium chloride. It is the attraction between these different charges that holds these two respective ions together to form an ionic bond. Here you have the formation of a salt crystal. It forms a nice little crystallized structure. Alright, so far we've talked about nonpolar covalent bonds, polar covalent bonds, and ionic bonds. Alright, so we talked about the equal sharing, the sometimes, not always sharing, but still sharing, and completely giving away electrons to another respective atom, ionic bonds. There are other types of chemical bonds in nature. Alright, so for instance, you have weak chemical bonds. Alright, we have hydrogen bonds, and we have something we call van der Waals forces. Alright, so that's what we're going to talk about next. Now, weak chemical bonds are important. Alright, because a large proportion of your biological molecules are held together by these weak bonds. Alright, so for instance, things like your proteins and your DNA are held together by hydrogen bonds and other types of weak bonds. Alright, now, the cool thing about these weak bonds is that collectively as a whole, they're strong. But they can also be broken, so it's reversible. Alright, so looking at hydrogen bonds. Alright, so with hydrogen bonds, you have, for instance, water and ammonia. Alright, so you have two molecules, alright, that contain two highly electronegative atoms. Alright, they also are covalently bonded to hydrogen. Alright, so here, when you look at water, water is bound to oxygen, which is highly electronegative, and hydrogen, which has a slight positive charge. Alright, so nitrogen's also highly electronegative. And nitrogen, not so much. So it gets a partial charge. Alright, so it is the interaction between these charges, between a hydrogen atom and this highly electronegative nitrogen. The bond that forms between them is a hydrogen bond. Now, hydrogen bonds will break and form. Break and form, break and form, break and form. Alright? They're not static. They don't always hold on to one another. Alright? They're weak bonds. Alright? The two molecules can pull away from one another. Van der Waals forces. Alright? Van der Waals forces has to do with basically if you have a molecule like HCl. Alright, so you recall that HCl was a polar molecule. It's held together by polar covalent bonds. Alright, so two molecules of HCl. Alright, they can interact with one another, whereby, for instance, alright, due to the location of their electrons. Alright, so the electrons are spending more time around the chlorine atom and less time around this little hydrogen. Okay? So you get this weak interaction between the chlorine with a negative charge, partial negative, and you get the hydrogen with a partial positive. So there's an attraction. Now these electrons, there's a higher amount of electrons, higher density of electrons around the chlorine, and less around the hydrogen. But the electrons don't always stay with the chlorine atom. Alright, they can go back to the hydrogen. Alright, because they're being shared. It's a covalent bond. Alright, so basically for a period of time, this negative charge can disappear. So this bond will break, but then it can reform once the chlorine atom takes back the electrons. Alright, so van der Waals interactions are weak chemical reactions. So it has to do with the attraction between molecules that are close enough together and are interacting and holding on to one another as a result of these charges. Okay, so we're going to transition away from talking about chemical bonds, and we're going to talk about now shapes of molecules and how this is related to their function. Alright, so what determines the shape of a molecule? Well, it has to do with, one, what particular atoms are found in that molecule. And it has to do with the particular properties of each of those atoms. Alright? Has to do with their electronegativities. Alright? Are electrons being equally shared or unequally shared in a molecule? So, and due to these possible charges, right, this is going to affect the overall shape. Alright, so molecules are going to arrange themselves so that there's the least, basically, resistance. So that everybody's happy in a molecule. Because in some parts of a molecule you can have positive charges and negative charges, and you don't want two negative charges being too close to one another because there's a repulsion. You don't want two positive charges being too close to one another because there's a repulsion activity that's going on. So atoms are going to orient themselves and arrange themselves so that they're equally spaced away from one another. So they're all happy, they're all interacting, but they don't want to be too close. Right, so here you're being shown a representation of, for instance, atoms in a particular molecule. They're forming a tetrahedral shape. Alright, so it's kind of like carbon, hydrogen, alright, methane. They form a nice little tetrahedron shape. Alright, looking at water. Alright, so there's a particular reason behind this distance between two hydrogen atoms, which is 104.5 degrees. Right, so it's because hydrogen, well, it's got one proton. You don't want these two atoms being too close to one another. Alright, they're going to repel one another. So there's a certain distance away from them that's going to promote this. So you get this nice little V shape to the water molecule. Alright, so looking at the biological application of molecules and the shape and the function. Alright, so looking at two drugs. Alright, you have something like morphine. Morphine and endorphins. Alright, they have similar effects because of their molecular shape. And they bind to a particular receptor in the brain. Alright, so here you have endorphins and morphine. Alright, notice here you have this chemical group of carbon, oxygen, and hydrogen. And here you have this chemical group of the same thing, carbon, oxygen, and hydrogen. Alright, they look very similar to one another. Obviously, endorphins, very different from morphine. Alright, but the key part here is this group and this group. Because this is the group, or part of the molecule, that binds to the receptor of a protein in a cell, in a brain cell. Alright, so this is basically the key, and the protein and the binding site is the lock. So the shape of a molecule, even though they could be completely different, alright, if there's a part of that molecule that resembles the particular binding site of something, that's a chemical that is involved in transmission of information or signals, or it's a hormone, alright, it binding to this binding site of a protein in the membrane of a cell, alright, there could be competition, because there could be other molecules in nature that look very similar to it. Alright, because think about it, endorphins. Endorphins are natural painkillers, right? But so is morphine. So morphine isn't natural, right? But it's a drug. It's a painkiller. Right? They bind to the same site in the brain. They bind to the same receptor. And it's all due to their shape. Alright, so looking at chemical reactions, the making and breaking of chemical bonds. Alright, so chemical reactions, you have reactants, whatever you're starting with, and the products, what you're trying to form. Right now, there's this law of conservation of matter. Alright, so the law of conservation of matter states that matter cannot be created or destroyed. Alright, so chemical reactions, you don't create stuff spontaneously, and you don't destroy matter. In a chemical reaction, all you're doing is basically breaking and forming chemical bonds between atoms. Alright, so here you're shown different types of chemical reactions. Alright, so you have, in this first process, reactant A and B. Alright, they're being joined together to form product AB. You can have AB that breaks off into A and B. So one involves the forming, one involves the breaking of bonds. Alright? You can have a rearrangement reaction where you have AB plus C. Right? Well, C joins with A, and B is an additional product that's left over. You can have a double rearrangement. You have AB and CD. You form AC and BD. Alright, so there are different types of reactions. Alright, so looking at the formation of water. Alright, so here, alright, you have a molecule of hydrogen gas. You have a molecule of oxygen gas. And you have a molecule of water. Alright, so looking at this molecule of water, notice that it has two hydrogen atoms. All right, that's what this little subscript means, and it has 1 oxygen atom. Notice that your molecules of hydrogen gas and oxygen gas. Hydrogen gas has 2 atoms of hydrogen. The oxygen has 2 atoms of oxygen joined together. Alright, so H2, H2, O2, and water. Alright, so all you're doing is breaking chemical bonds, breaking this, breaking this, breaking this, rearranging the atoms to form a new product, water. Alright, so here you're being shown the same thing as you saw here. Alright, so you have hydrogen gas, oxygen gas, and water. Alright, so you have to physically break the chemical bond, the covalent bond between the hydrogen atoms. You have to break the chemical bond between the oxygen atoms so that you can form new covalent bonds between the hydrogen, oxygen, and oxygen of a water molecule to form a water molecule. Alright? So chemical reactions, you're doing nothing more than breaking and forming new chemical bonds so that atoms are rearranged. Alright? You're not creating new atoms out of nothing, and you're not losing atoms. Alright? Everything has to be balanced in a chemical reaction. Alright, so coming back to this idea of balanced chemical reactions. Alright? So balancing chemical reactions. Alright, so for the time being, kind of disregard this here. Alright, I'm going to go through a series of steps to show you how to balance a chemical reaction. Alright, so the idea of balancing a chemical reaction. Alright, the total number of atoms you start with in your reactants, you have to end with the same total number of atoms. Based on this law of conservation of matter. So, here, initially, right, looking at the reaction, when it's unbalanced, alright, you have hydrogen gas, oxygen gas, and water. Alright, so, looking at your reactants, you have 2 atoms of hydrogen. You have 2 atoms of hydrogen in your product. Alright, here, oxygen. You have 2 atoms of oxygen as a reactant, but in your product, initially, you have 1 atom. Alright, so this is a unbalanced chemical equation. You have to balance it. So how do you go about balancing a chemical reaction? Alright, well, let me show you. Alright, so initially, alright, you have 2 hydrogen atoms and 2 oxygen atoms. Alright, so again, the subscript tells you how many atoms of a particular element you have. Alright, so you have 1 molecule of hydrogen gas right now, 1 molecule of oxygen gas. Well, a molecule of hydrogen gas has 2 hydrogen atoms. A molecule of oxygen gas has 2 oxygen atoms. And then here, initially, you have 1 molecule of water, which is made up of 2 hydrogen atoms, 1 oxygen. Alright, so initially, what I would do to balance this reaction is, since you have initially 2 hydrogens over here, you have 2 hydrogens as a product and 1 oxygen. Well, since you have 2 oxygens as a reactant, what can you do? Well, you can put a 2 in front of the water. Alright, so that gives you now 2 molecules of water. Alright, so if you have 2 molecules of water, alright, notice here, 2 molecules of water means that you have 1, 2, 3, 4 hydrogen atoms. And you have 2 oxygen atoms. Alright, so 2 molecules of water gives you 2 oxygen atoms and 4 hydrogens. Alright, so we have 2 hydrogens now, or 2 molecules of water, so that means we have 4 hydrogen atoms. Alright, so now the left side of the reaction, the reactants, is what's off a bit. Alright, so how do we fix that? Well, you don't have to, because now, well, actually, it's not balanced. That's not balanced. Sorry. Slides are a little off there. Here, alright, you'll see you have 4 oxygen atoms on the right. Alright, disregard that this reaction is balanced because it's not yet. Okay. What you would do is, to correct for this, you would throw a 2 in front of the hydrogen gas. Alright, so that gives you 2 molecules of hydrogen gas. Well, if you have 2 molecules of hydrogen gas, you got 1, 2, 3, 4 molecules or 4 atoms of hydrogen. Alright, so now 4 atoms of hydrogen, check, check. 2 oxygen atoms reactants, 2 oxygen atoms products. Everything is nice and equally balanced. Okay. Alright, so looking at the next chemical reaction. Alright, so looking at taking something like glucose. And in this case, you're left with ethanol and CO2. Alright, so how would you go about balancing this reaction? Alright, well, first you have the reactants. Alright, you have, looking at carbon, you have 6 carbon atoms, 12 hydrogens, and 6 oxygen atoms. Well, looking at your products, right, well, you got here 2 oxygens in the ethanol, or 2 carbons in the ethanol, sorry, and 1 carbon atom in the carbon dioxide. Alright, so that gives you, that would give you initially, that would initially give you your 3 carbon atoms. Right? Now, hydrogen, you have 6 atoms of hydrogen, and in oxygen you have 3. Alright, so you have 2 oxygen atoms in CO2, 1 oxygen atom in the ethanol, so that gives you 3. Alright, so how should you go about balancing this particular equation? Alright, well, you know here that on the left side of what you start with, there's your reactants, you have 12 hydrogen, right? Well, you get 6 oxygen as a product. So what you can do is you can throw a 2 in front of the ethanol. Alright, and so that's going to give you now 2 times 2 molecules of ethanol is going to give you now a total of 4 carbon atoms, and you still have this 1 carbon atom in CO2. Alright, which gives you 5 atoms of carbon. Alright, well, 2 times 6 for the hydrogen gives you 12 hydrogen atoms, and now you have 2 molecules of ethanol. That means you have 2 oxygens from the ethanol, you have 2 oxygens from the CO2, that gives you 4 oxygens. Alright, so this equation is still unbalanced. Alright, so how do you balance this up? Alright, so what you would do next is you have to put a 2 in front of the CO2. Alright, so putting a 2 in front of the CO2 gives you now 6 carbon atoms. Because 4 carbon from the ethanol plus 2 carbons from the CO2 gives you 6 carbons. Alright, which is what you have in your original reactant of glucose, 6 carbons. Okay, well, your hydrogen atoms are balanced. That's good. And then looking at your oxygen, right? So you have 2 atoms of oxygen in ethanol. And you have 4 oxygen atoms and CO2, because you have 2 molecules of CO2. Alright, so 4 oxygen plus 2 oxygen is going to give you 6 oxygen atoms. Alright, so now the number of atoms you start with is balanced with the number of atoms you have in your products. So now your equation is balanced. Alright, so moving on to this last example for balancing chemical equations. Alright, so you have iron, you have chlorine, and you have iron chloride as your product. Alright, so notice here, you have an atom of iron, you have 2 atoms of chlorine, and you form iron chloride. Alright, so here are your initial reactants. Right, 1 atom of iron, 2 atoms of chlorine. Your initial products, 1 atom of iron, and 3 atoms of chlorine. Alright, so how do you go about balancing this equation? Alright, so here, if you put a 2 in front of the iron, you end up with 2 atoms of iron and you have 2 chlorine atoms as your reactant. Alright, well, you still have 1 iron atom and iron chloride, and 3 atoms of chlorine. Alright, so you'd have to throw a 2 in front of the iron chloride and your product. And now you have 2 atoms of iron, which balances out with your initial reactant. But then you gotta look at your chlorine. Well, your chlorine atom in your product has 6 chlorine atoms. Alright, well, that would mean that you'd have to have 6 total chlorine atoms in your reactants. So how do you get that? Well, you put a 3 in front of the chlorine in reactant, and everything balances out as it should.